When you open Wireshark and start a capture on a busy network interface, you are immediately flooded with hundreds or even thousands of packets per second. Without a way to narrow down what you see, finding the traffic you care about becomes nearly impossible. This is where filters come in, and more specifically, Berkeley packet filter syntax, which is the foundation of Wireshark's filtering capabilities. Berkeley packet filter, often abbreviated as BPF, is a low-level filtering language originally developed for Unix systems. It allows you to describe, in a compact and readable way, exactly which network packets you want to capture or display. Wireshark uses this syntax in two distinct contexts: capture filters and display filters. Understanding the difference between these two is the first critical concept of this chapter. Capture filters versus display filters. A capture filter is applied before any packet is recorded to memory or disk. When you set a capture filter, Wireshark instructs the underlying network driver to only hand over packets that match your criteria. Packets that do not match are simply discarded and never stored. This is very efficient when you know exactly what you are looking for, because it saves memory and processing power. The downside is that once a packet is filtered out at capture time, it is gone forever for that session. A display filter, on the other hand, is applied after packets have already been captured and stored. All packets are kept in memory, but only the ones matching your display filter are shown in the main packet list. You can change, add, or remove display filters at any time without losing any captured data. This makes display filters much more flexible and forgiving during analysis. For the purpose of this chapter, we focus on Berkeley packet filter syntax, which applies primarily to capture filters. However, many of the concepts overlap with display filters, which use Wireshark's own extended syntax that we will also cover here because practitioners use both daily. The structure of a Berkeley packet filter expression. A Berkeley packet filter expression is built from three types of primitives: type, direction, and protocol. Type qualifiers describe what kind of entity the filter applies to. The most common types are host, for a specific IP address or hostname; net, for a network range; and port, for a specific port number. Direction qualifiers describe the direction of traffic relative to the entity you specified. The most common directions are SRC, source, DST, destination, or no qualifier at all, which means both directions. Protocol qualifiers restrict the filter to a specific protocol. Common ones include Ether, Ethernet, IP, Internet Protocol version 4, IP6, Internet Protocol version 6, TCP, Transmission Control Protocol, UDP, User Datagram Protocol, ICMP, Internet Control Message Protocol, and ARP, Address Resolution Protocol. These primitives can be combined using logical operators, and both conditions must be true, or at least one condition must be true, and not the condition must be false. You can also use parentheses to group conditions and control precedence. Essential capture filter examples. Here are the most common and useful Berkeley packet filter capture filters you will encounter and use as a cybersecurity practitioner. Filtering by host. The expression host 192.168.1.10 captures all packets going to or coming from the IP address 192.168.1.10. If you only want traffic originating from that address, you write src host 192.168.1.10. If you only want traffic destined for that address, you write dst host 192.168.1.10. Filtering by network. The expression net 192.168.1.0 out of 24 captures all packets to or from any address in the 192.168.1.0 out of 24 subnet. This is useful when you want to monitor an entire local network segment rather than a single machine. Filtering by port. The expression port 80 captures all packets where either the source or destination port is 80, which is the standard port for unencrypted hypertext transfer protocol web traffic. To capture only traffic going to port 80, you write DST port 80. To capture encrypted web traffic over hypertext transfer protocol secure, you would use port 443. Filtering by protocol. The expression TCP captures only transmission control protocol packets. Similarly, UDP captures only user datagram protocol packets, and ICMP captures only Internet Control Message Protocol packets such as ping requests and replies. Combining filters. You can combine any of the above using logical operators. For example, TCP and port 443 captures only transmission control protocol packets on port 443. The expression host 10.0.0.5 and not port 22 captures all traffic to or from 10.0.0.5, except traffic on port 22, which is used by Secure Shell. The expression TCP and port 80 or port 443 Captures transmission control protocol traffic on either port 80 or port 443. Filtering by MAC address, Ethernet layer. The expression etherhost 00:1A:2B:3C:4D:5E captures all packets sent to or from the device with that hardware address. This can be useful when you're investigating a specific physical device on the local network. Wireshark display filters, a richer syntax. While capture filters use strict Berkeley packet filter syntax, Wireshark display filters use a more expressive language specific to Wireshark itself. These are the filters you type into the filter bar at the top of the Wireshark window after a capture has started or ended. Display filters use field names based on the protocol dissectors built into Wireshark. Here are the most important ones you need to know. Filtering by IP address. The display filter IP.address == 192.168.1.10 shows all packets where either the source or destination IP address is 192.168.1.10. For only source addresses, use IP.src == 192.168.1.10. For only destination addresses, use IP.dst == 192.168.1.10. Filtering by protocol. Simply typing TCP in the display filter bar shows only transmission control protocol packets. Typing UDP shows only user datagram protocol packets. Typing DNS shows only domain name system packets. Typing HTTP shows only hypertext transfer protocol packets. Typing TLS shows transport layer security packets, which carry encrypted hypertext transfer protocol secure traffic. Filtering by port. The display filter TCP.port == 80 shows all transmission control protocol packets on port 80. Using TCP.dst port == 443 shows packets destined for port 443. Using UDP.port == 53 shows all user datagram protocol packets on port 53, which is used by domain name system. Filtering by transmission control protocol flags. This is especially useful in security analysis. The display filter TCP.flags.syn == 1 shows all packets with the synchronized flag set, including the first step of a transmission control protocol handshake and potential port scanning activity. The filter TCP.flags.syn == 1 and TCP.flags.ack == 0 isolates only the initial synchronized packets, not the synchronized acknowledge responses. This combination is particularly relevant when you want to detect a synchronized scan performed by a tool like Nmap, which you have already practiced. Filtering by content. The display filter http.request.method == get shows only hypertext transfer protocol get requests. The filter http.response.code == 200 shows responses with a successful status code. The filter frame contains password searches the raw content of every packet for the string password, which can be useful in detecting credential leakage over unencrypted protocols. Negation and combination in display filters. You can use, or not to negate a filter. For example, ARP hides all address resolution protocol packets, which are often very noisy and distracting. You can combine filters with and vertical bar, or, for example, IP.address == 10.0.0.1 and TCP.port == 22 shows only secure shell traffic to or from that specific address. Practical use cases in security contexts. As a cybersecurity professional, you will rely on these filters in very concrete scenarios. Isolating a transmission control protocol handshake. After a capture like the one you performed in the previous activity, the filter TCP.flags.syn == 1 helps you identify all connection initiations, which is the foundation of detecting port scans or establishing which services were contacted. Detecting unencrypted credentials. A filter like HTTP and frame contains login or FTP can reveal plaintext authentication attempts. This is directly relevant when auditing insecure legacy applications. Analyzing domain name system traffic. The filter DNS isolates all name resolution requests and responses. During a penetration test, unusual domain name system queries, such as very long subdomains or queries to unexpected resolvers, can indicate data exfiltration or command and control communication. Following a single conversation. While not a filter per se, Wireshark's followed TCP stream feature, accessible by right-clicking a packet, effectively reconstructs a full exchange between two hosts, acting as a contextual filter around a session. It is built on the same underlying packet matching logic as display filters. Filtering noise during a live capture. During a penetration test or incident response, your capture will include broadcast traffic, address resolution protocol requests, and other background noise. A filter like Not ARP and Not Broadcast immediately reduces clutter and lets you focus on unicast traffic between specific hosts. Key points to remember. Capture filters use Berkeley packet filter syntax and are applied before packets are stored. They cannot be changed retroactively. Display filters use Wireshark's own syntax and can be modified at any time without losing data. The main Berkeley packet filter primitives are type, host, net, port, direction, SRC, DST, and protocol, TCP, UDP, ICAMP, etc. Logical operators or not allow you to build complex filters from simple ones. Display filter field names follow a dot notation based on the protocol, such as IP.address, TCP.flags.syn, HTTP.request.method, or DNS. Combining filters is essential in real-world analysis to isolate exactly the traffic relevant to your investigation. Knowing common port numbers, 80 for Hypertext Transfer Protocol, 443 for Hypertext Transfer Protocol Secure, 53 for Domain Name System, 22 for Secure Shell, 21 for File Transfer Protocol, is necessary to write meaningful port-based filters. Mastering these filters transforms Wireshark from a passive packet recorder into a precise diagnostic and investigative tool. Whether you are verifying that a transmission control protocol handshake is completing correctly, hunting for suspicious traffic patterns, or validating that your application does not leak sensitive data in clear text, the ability to write and combine filters quickly is a fundamental skill for any cybersecurity or DevSecOps practitioner.